All right, so we're going to finish the 9.4 notes here. So we're going to look at absolute convergence and the ratio test. So for absolute convergence, this is if we take the series of the absolute value of our sequence. If that converges, then the original series converges. So absolute convergence is a really nice test for when you have terms that are maybe alternating in sign between positive and negative. And we want to just ignore that and look at the sequence itself as positive numbers and see if we get convergence. So for the first example here, we've got that we want to show that the power series from n equals 0 to infinity of cosine x to the n over n factorial converges for all x. So meaning irregardless of the value of x, will this always converge? We can see that this is going to converge because this is equivalent to the power series for e to the cosine x, which converges for all x. So this is going to be a pretty easy one to determine convergence for. So if we think of tests we could use, this is not geometric. The nth term test won't work because the sequence goes to 0. And then if we were looking at a comparison test, though, it looks like we could probably come up with a pretty good comparison test. So what we'll note is that cosine x is between -1 and 1, obviously. So the numerator is really going to be some number between -1 and 1 for all n and for all x, which is really nice. So note this is for all x. So let's go ahead and consider the absolute value then of our series. Okay, so if we take the absolute value, we know that this is going to be less than or equal to, I guess we could say, but it'll be less than or equal to 1 over n factorial. And so 1 over n factorial is going to be a convergent series. We can prove this a number of ways. One would be that this is going to be less than 1 over n squared, let's say. All right, so n factorial is going to be much bigger than n squared at a certain point in the series. So by comparison, by the comparison test. So we could do like a comparison test here to show that this converges absolutely. The other way we could do it is with the ratio test, which we'll look at in a moment. And I guess I should add here the p-series test, which will prove the p-series test, or I'll prove it maybe in a separate video, but the p-series test uses what we call the integral test, which is if an integral can be used to bound a sequence of terms and it converges as an improper integral, then the series will converge as well. So p-series is, if we consider any series where it looks like 1 over n to the p, where p is greater than 1, then we'll get convergence. So 1 over n to the p converges. So that's our p-series test. Now if p is equal to 1, obviously it's the harmonic series and it diverges, and if it's between 0 and 1, so some root function, it's also going to diverge. So p-series is a super nice series for the comparison test. All right, so let's get to the ratio test. This one's going to be really nice for us as well. So let's let a sub n be a series with positive terms, and the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L, then the series converges if L is less than 1. The series diverges if L is greater than 1, and the test is inconclusive if L equals 1. So L equals 1 means it could be divergent, it could be absolutely convergent, and it could be what we call conditionally convergent. So those we'll discuss in the next set of notes. But the key idea is that we just really have to take this ratio and consider what this ratio looks like. So let's go ahead and start with A. We've got this power series n factorial x to the n. So if we apply the ratio test here, so by the ratio test, we'll get the limit as n goes to infinity. Let's make some spacers here. So we want the n plus 1th term over the nth term. So that's going to be n plus 1 factorial x to the n plus 1 over n factorial x to the n. So let's go ahead and see what that gives us. So we'll have n plus 1 factorial is equal to n plus 1 times n factorial, since it's just subtracting one integer down each term. So we'll get some nice cancellation here, and we'll just have an n plus 1. And then the x to the n is going to cancel and leave us with just an x. So we're going to have n plus 1 times x. So now if we take the limit as n goes to infinity, well, n plus 1 is going to go to infinity for sure. And then x, well, the only value of x for which you could have convergence is going to be for a specific value. So we'll just note this is going to have two outcomes. It's going to be infinity or negative infinity if x is not 0. All right, so for any number x that is not 0, we're going to get infinity or negative infinity, which means divergence. And then it's 0 if x equals 0. So we'll just note, so this series diverges, because we'll note infinity and negative infinity are both greater than 1 in absolute value. So again, if we're taking the absolute value, oh, that's what I forgot. So note, we're going to take the absolute value of these terms. Yeah, so we'll consider the absolute value. So we don't end up with a negative value of L. So that's clearly going to be greater than 1 when we take the absolute value, because we'll just have infinity. So the series diverges for all x except x equals 0. And so that means that the radius of convergence is equal to 0. So r equals 0. So for a power series will always converge at its center. So the center of this power series is obviously going to be x equals 0. And the reason why it converges is because it makes your series identically 0 everywhere, right? So you'll have zeros everywhere. And so if we have zeros everywhere, then we end up with a number, which means we have convergence. We'll end up with a finite term, which is convergent. So our radius of convergence is 0, which means it converges at x equals 0 only and diverges for all other values. All right, so for B, we've got a mixture of a linear term, a log, and an exponential. So seems like this should probably converge because that 2 to the n is going to grow really, really fast compared with n and ln of n. So let's look at the ratio test. we've got the limit as n goes to infinity of n plus 1 times the natural log of n plus 1 over 2 to the n plus 1. So all of that is going to be over n ln of n and 2 to the n. So in these fractional expressions, we're just going to use reciprocation. So we'll have n plus 1, natural log of n plus 1, over 2 to the n plus 1. I might run out of space here. Let's see. Times 2 to the n over n times the natural log of n. Just enough space to fit. All right. So we've got, the 2 to the n will cancel. And let's see what we end up with. So this is going to equal the limit as n goes to infinity of n plus 1 natural log of n over 2n, n plus 1 natural log of n. And so we can do L'Hopital's rule here if we wanted to. What we'll see is that the leading terms are essentially equal in degree because this natural log of n plus 1 and natural log of n are equivalently the same size. So this limit is going to equal 1 over 2. Which is less than 1. So thus, converges. And one other note on part A, we would say converges. Oh, actually, let's leave that off for now. We'll come back to that though. All right, so let's look at C and D. So for C, we've got e to the n squared over n factorial. So let's take a look at our limit here. So we'll have e to the n plus 1 squared over n plus 1 factorial. Then I'm just going to multiply by that reciprocal. All right, so we've got e to the n squared in the denominator, n factorial here. So now we're going to have to kind of work with properties of exponents a little bit, be a little bit careful with our work. So we'll get the limit as n goes to infinity. So we'll have e to the 2n times e squared. Since, oh, no, sorry. Let's put the squared term in front. So e to the n squared times e to the 2n times e squared. Our n factorial is going to cancel with the n plus 1 factorial, leaving us with an n plus 1. So we'll have n plus 1 e to the n squared, and then our e to the n squared will cancel. So we've got e to the 2n times e squared. And n plus 1. And again, we can apply L'Hopital if we wanted to. So we get 2e to the 2n over 1 times e squared. But again, if you see what the answer should look like, you can just jump to your final value, which is that this is going to equal infinity. So this does not exist. It's clearly going to be greater than 1. This diverges. So the series is going to diverge. So we've got a convergent series, a divergent series, a series that converges as a power series at radius of 0, and then D, we've got this cosine 1 over n. So let's take a look at this. So this would be an example where we couldn't use the ratio test. Right? So we'll note cosine 1 over n is going to alternate between positive and negative numbers as n changes, right? So as n is changing, it's going to alternate, or is it? Right? So note 1 over n, it's going to approach 0. So it looks like these are positive. So why don't we take a look at the ratio test itself? So let's take the limit as n goes to infinity of, so cosine 1 over n plus 1, cosine 1 over n, as n goes to infinity, right? It looks like this is going to equal 1. So this is inconclusive. So we can apply the ratio test here, but it's going to be inconclusive. And so this would be a series where we would want to use some other type of test for cosine 1 over n. And we'll note that we could do it by comparison possibly to see if we could bound it below or above. But actually, if we take the limit of the sequence, we can see that that's equal to 1. Thus, by the nth term test, the series diverges. So we're going to want to fall back on what we used previously if the ratio test fails. There will be other tests as well that we can use, but the nth term test and comparison test are going to be ones that show up quite a bit. All right, so that concludes our ratio test examples. These are going to be ones that, again, you want to kind of work with and find the ones that work well, and the ones that don't work or fail to work, you'll have to rely on other tests to prove either divergence or convergence. All right, so that concludes our notes here. So if you have questions, shoot me an email. Otherwise, come by my office hours. And until I talk to you next time.